My name is Wenhao Sun, and I'm an assistant professor in the Department of Material Science and Engineering. Here at the University of Michigan, I lead a computational material science research group that aims to discover and design new materials for functional applications. Many research groups around the world use high-throughput computational material science to predict new materials that have superlative properties for, say, batteries, solar cells, thermoelectrics, superconductors, and materials of that type. However, even though you can use thermodynamics to predict the existence of these wonderful materials, when people go to the laboratory to try to synthesize them, oftentimes they find that they cannot actually make these materials that were predicted. In our group, what we do is we try to develop new fundamental theories of synthesis science and materials formation, nucleation, and growth to be able to predict synthesis recipes towards novel materials that were designed in a computer. If we can know what materials to make and how to make them, then we can fully close the computational materials design loop. When we talk about developing predictive theories of material synthesis, there's really two categories we go for. The first one is understanding exploratory synthesis. In exploratory synthesis, we survey huge chemical spaces for new stable materials. We do this using high throughput DFT computations, and then we use materials informatics methods to construct large stability maps that give us a sense of which regions of chemical space are stable, which regions are metastable, and which regions might be unstable. When we pass these maps on to our experimental colleagues, they can be guided by this insight to go to the laboratory and synthesize new compounds that have never been made before. And this accelerates from a traditional Edisonian approach to material search and discovery to a targeted, computationally driven, predictive mode of materials discovery.
Okay, so my research interest is in crystallization and nucleation and growth of materials. The problem that I'm working on right now is the dolomite problem. Dolomite is a calcium and magnesium double carbonate mineral. It is a very common mineral on Earth, but it doesn't precipitate under seawater even if it's supersaturated. What we're trying to do is we're trying to understand the thermodynamics of dolomite, and we're trying to predict the reaction of dolomite formation, and we're trying to explain why it's not forming in normal condition, and we're also trying to predict a condition that can form dolomite.
As we watch these observations of materials forming, one thing that we're recognizing is that as materials nucleate and grow at the nanoscale, there are other forms of work that are operative during their formation that we haven't taken into account. Things like surface energy, electrostatics, strain energy, electromagnetics, electrochemical work. And these are things that if you input into the free energy expression of materials, grows that free energy expressions into very high dimensional spaces. If we can calculate phase diagrams in higher dimensions that have axes of forms of thermodynamic work that are not typically accounted for, work like elastic work, surface energy work, electromagnetic work, then we can even rationalize the formation of what we thought to be metastable or non-equilibrium phases, but these are phases that are actually stable at the nanoscale where they nucleate under those applied forms of thermodynamic work.
My research is in the structure selection of systems that can have a range of different structures, specifically vanadium oxides, which are very important in electronic and magnetic applications. We're currently trying to develop computational methods of predicting which structure and phase of vanadium oxide will show up when we try to synthesize it.
When ternary diagrams are taught in classes, they're often taught in a sort of 2D form. You see them in books, on pieces of paper, projected up on screens, and it's very hard to understand what's going on in kind of the 3D space that they're supposed to be in, and you have to do a lot of mental visualization to understand the different compositions and how they interact with temperature. So by taking this 2D diagram and placing it into a 3D space where it's supposed to be, such as VR, we can interact with it and walk around it and really get a much better feel for how it's supposed to be interpreted and get a wealth of information that we wouldn't have been able to get from a 2D representation of it.
Altogether, our research directions really combine to integrate into materials science and engineering. Materials science is where we understand how materials form, and materials engineering is the aspect of designing new recipes to make the materials that we have predicted to be stable. We're always looking for passionate and motivated undergraduate and graduate students to join our research group. Here we use applied thermodynamics, high throughput density functional theory, and materials informatics to understand how materials form and to be able to design new ways to synthesize the materials that are going to drive the energy revolution in the future.